Hello everyone, welcome to Physics 205. So in this video, I want to go over the in-class practice problems for vectors. These are sort of like some of the general vector type questions. So this first question says, an offensive lineman for the Patriots is faced with blocking two of the Eagles' defensive linemen. If the Patriots lineman pushes forward, assuming the forward direction is along the positive x-axis, with a force of 100 pounds, while one of the Eagles pushes at 120 degrees with a force of 50 pounds, and the other pushes at 250 degrees with a force of 75 pounds. The question is, does the offensive lineman stop the two Eagles? Like, does the lineman move forward? And if not, what is the resultant force? Actually, I guess if they're asking whether the lineman stops two Eagles, they want the net force to be 0. Okay, and if not, then what is the resultant net force? Okay, so what I would do is, to start, let's just draw this out to get an idea of what's going on here. So here's my coordinate system. And then we'll do this graphically. Actually, we'll do it both graphically and analytically. We'll do it both ways. So first of all, the Patriot is pushing along the positive x direction, right? So let's say this is P for a Patriots player. And we know that is 100 pounds. So the magnitude of P is 100 pounds. Then we have the Eagles player, I call it like E1, is pushing at 120 degrees with a force of 50 pounds, right? So 120 degrees is something like this. Right, where this is 120. So I'll call this like E1. And the magnitude of V1 is 50 pounds. And then finally, the other Eagles player is pushing at 250 degrees, which is going to be in the third quadrant, kind of like this. So this is E2. This angle right here would be 250 degrees. And then that magnitude of E2 is 75 pounds. Okay, so what we want to do is, these are like 3 force vectors. We want to add them both graphically and then analytically and see if we get a result of 0, right? Then they're exactly stopped, or if we get a resultant vector. So if you just kind of do this by sketching it right now, it looks like there is going to be a resultant vector, right? Again, it's hard. We won't know for sure until we draw this out perfectly or do it out analytically. But if I just sketch it, I'm starting with P. I'm going to move the tail of E1 to the tip of P. So it'll look something like this. And then the tail of E2 to the tip of E1. So it'll go something like this. And it looks like I'm going to have a resultant vector somewhere in like that 4th quadrant. So this is like R, where R in this case is P plus E1 plus E2. Right? If that had added to 0, if they all had met back at the origin here, then I know that there's no net force, right? Then you could say the Patriots players stopped the other two. But in this case, it looks like they're moving kind of forward, but they're moving at an angle here. So it looks like there is a resultant force. That's the resultant force that we want to find. Okay, so first thing we should do actually is choose some conversion factor. Oh, it looks like we already have, it's going to be 1 centimeter is 20 pounds. I already have that written here. So let's convert all these forces into centimeters. So I'll start with magnitude of P, which is 100 pounds. I want to multiply by 1 centimeter over 20 pounds. So that'll be what, 5 centimeters. Then I have E1, which was 50, right? 50 pounds times 1 centimeter over 20 pounds. That's going to be 2.5 centimeters. And then E2, I just want the magnitude of E2, so I don't need a vector there, is 75 pounds. And 1 centimeter is 20 pounds. So that's going to be just under 4, like 3.75 centimeters. Okay, so let's go ahead and add these graphically. So I'll do this first graphically on the graph paper. Okay, so we'll start with the Patriots force vector, which is going to be, what was it, 5 centimeters, and it's right along the positive x-axis, right? So something like this. That's P for Patriots. And then the eagle. So I'm going to draw like a new little coordinate system there at the tip of P. And now at 120 degrees, we have the first eagle player. So 120 is like here. And that was what? That was only like 2.5 centimeters, right? So I'll go up. I'll start at 8 and go to like 5.5, something like that. So that's E1. And then from there, I have like a new coordinate system. Again, I'll just dash it in here. And now I want 270 degrees. So I need to go basically like 180 plus, no, 250, right? 250 degrees. So 180 plus another 70. So I have to flip this over and then go down 70 degrees. So something like that. And that was 3.75 centimeters. So right about there. So that was E2. And then finally, if I draw a vector from the tail of P, that first force vector, right, from the origin to the tip of the last one, that'll be my resultant. Okay, if I measure this, it looks like I got maybe 2.8 centimeters. So I'm going to say R is 2.8 centimeters. I'll convert that right back to pounds. So 20 pounds is 1 centimeter. So that's going to be 56 pounds. And if I measure that angle, again, it's hard to tell, right? You'd have to really like kind of extend this out to get a good measurement. If I extend this, if I dash this out further, and if you measure that, it turns out it's around 30 degrees. At least when I did this carefully, I got like 30 degrees. So this angle right here, we're going to say is like 30 degrees. So that means that resultant force there is going to be 56 pounds at 30 degrees south of east. Or if I wanted to give this angle, that would be 360 minus 30, which would be 330 degrees. Right, so I could say R is equal to 56 pounds at 330 degrees. Okay, so that's graphical, right? Which is not the most accurate. You get a really good sense of what that net force should be, but it's not the most accurate. The most accurate way to do this is analytically. So let's actually do it analytically next. So I'm going to go back to the iPad to do this analytically. Okay, so to solve this problem analytically, to add those three forces from the Patriots and the two Eagles player analytically, we have to first find the components, right, of each force vector. So to do that, let me just draw these out. Remember the Patriots, it was right at like 0 degrees. And we know that magnitude was 100, right? It was 100 pounds. So that means P is going to be, if you want, you could say Px, the x component is positive 100, and the y component was 0, right? All that vector is in the x direction. None of it is in the y direction. So P itself, you could write, if we want to use unit vectors, it's 100 I hat plus 0 j hat. And this has units of pounds. Okay, then we do E1, the Eagles player, that force. So that was 120 degrees. So it's like this. So remember E1 was, I think it was 50 pounds. If this angle is 120 degrees, that means the reference angle here, if we want to use this reference angle, is 60 degrees. And we want to find the components, right? So we want to find E1x, which is going to be negative, and then E1y, which will be positive. Now remember, there's so many different ways of doing this. The easiest might be just to extract out that right triangle that contains the reference angle. Where this is 60 degrees. This is E1y. This is E1x. And in E1, we know that magnitude, this is 50. So the hypotenuse is 50 pounds. So then if we want E1x, since it's adjacent to the 60 degrees, we need cosine, right? So it's going to be 50 times cosine of 60, but we know it's pointing to the left, right? That component's to the left. So it's actually negative. So it's going to be negative 50 times cosine of 60 degrees. And that equals negative 25. And then E1y will be positive, and since it's opposite to 60, right? It's going to be using sine, right? Opposite over hypotenuse. And it's positive because it's pointing upward. It'll be 50 times sine of 60. And that's equal to 43.3 pounds. So then I could write E1 as negative 25 I hat plus 43.3 j hat pounds. And then finally, E2, do that over here. That was pointing in the third quadrant like this. The magnitude was, I think it's 75 pounds. Yeah, 75 pounds. We know this angle was 250 degrees, which means this angle right here is going to be 70 degrees, right? The reference angle. And again, I want to find the x component. This is E2x, and then the y component. E2y. So if I extract out the right triangle that contains the reference angle, then this is E2x, E2y. The magnitude was what, 75 pounds? And I know this angle right here is 70 degrees. Okay, so if I want to find the x component, first of all, it's negative, right? It's pointing to the left. And it'll be 70 since it's adjacent, it's going to involve cosine. 70 times cosine of 70 degrees. So that'll be, wait, I made a mistake here. The magnitude is 75, right? This should be 75. It's negative and then times cosine of 70. Yep, that's right. So negative 25.65 pounds. And then E2y is also negative, and it's 75 times sine of 70. And that ends up being negative 70.48. So E2, I'll just write it in unit vector form. It'll be negative 25.65 I hat minus 70.48 j hat. The other way you could do this is you could make a table, right? And you could keep track of the x components and y components. Remember, there's multiple ways of adding these vectors together. Okay, so now R, my resultant vector, is going to be P plus E1 plus E2. So P though was what? It was, oh yeah, 100 I hat plus 0 j hat. E1 was negative 25 I hat plus 43.3 j hat. And then E2 over here was negative 25.65 I hat and then minus 70.48 j hat. So if I add them, remember when you add vectors together, you're adding the components, right? So I'm adding the I hats and then adding the j hats. So really this will be like 100 minus 25 minus 25.65 I hat. And then plus, and now we do the j hats. I have 0, 43.3, and then minus 70.48 j hat. So if you work this out, this is going to be 49.35 I hat, and then it'll be actually minus 27.18 j hat pounds. Okay, so that's our answer. It's in component form. Let's convert it to polar form. So if I were to draw this out, right, it would have an x component that's positive. This is like Rx, 49.35. And a y component, it's negative. So negative 27.18. So that means the actual vector is in this fourth quadrant here, which is what we found graphically, right? So that's R. And we want to find the magnitude, and we want to find this direction. So again, if I extract out that right triangle, now that I'm just dealing with triangles, I can just keep these as positive, right? This is 49.35. This is 27.18. I want to find R, that magnitude. I want to find this angle, theta. So how do I find the magnitude? Pythagorean theorem, right? So I know R must be the square root of the x component squared, so rx squared plus ry squared. Just Pythagorean theorem, right? A squared plus b squared equals c squared, where c is r in this case. And if you work this out, this is going to be 56.3 pounds. And then to get the angle, I need to do inverse tangent of opposite over adjacent. And that turns out to be like about 29 degrees. And really, it's 29 degrees south of east, right? Because it's in that fourth quadrant. Okay, that's not bad, right? Because remember when we did it graphically, we got 56 pounds at 30 degrees south of east. So this is pretty close. So doing it analytically, we're getting R, that net force is 56.3 pounds at 29 degrees south of east. Or if you want, you could do 360 minus 29, right? And give the actual angle from the positive x counterclockwise. Either way is fine. Okay, great. Okay, in this question, okay, so in this question, question 2, it says, find the x and y components of the vector w, right, which is the weight of the object in the diagram below. So basically, in this case, see how the coordinate system is placed so that it's along the ramp, like the x coordinate is parallel to the ramp and the y coordinate is perpendicular to the ramp. And we know wx straight down towards the center of the earth. And we want to find the x component, we want to find the y component. So basically we want this, right? If I project this this vector onto the x-axis, I want this component, which is wx. If I project it onto the y-axis, I want this component, wy. I want to find those two components. It looks like wx will be positive, right? Because it's pointing along the positive x direction, and wy will be negative in the y direction. Okay, now there's options again here. See, so this ramp angle, 30 degrees, happens to be equal to this angle here, 30 degrees. So you could just use this right triangle here and use this angle, and that will work. Except in this case, the x component, which is this length, is going to involve sine, and the y will involve cosine, which is usually kind of the opposite of what we usually do, right? Usually what we do is we use a reference angle, which we could figure out here. If you do 90 minus 30, that this reference angle has to be 60 degrees. And then if we extract that triangle, so here I'll draw it out. So I have, here's W, this is 60 degrees, and then this is the right angle right here. So this is 60, this is W, this is WX, this is WY, right? And we know, do we have the magnitude? Yeah, magnitude of W is 20 newtons. So W is equal to 20 newtons. So this length is really just 20 newtons. So if we use that reference angle, then the x component will always involve cosine, right? Because it's adjacent to the angle. See how wx is adjacent to the 60 degrees? So then we could say, you know, the usual, we could say cosine of 60 equals adjacent over hypotenuse. And if I multiply both sides by 20 now, I'm going to have wx is 20 times cosine of 60 degrees. And if we work that out, that's going to be equal to 10 newtons. And it's positive because it's pointing down. And then if I do, if I want to find wy, now that's opposite the 60 degrees, so it's going to involve sine. So then I have sine of 60 equals wy over 20. So that means wy is equal to 20 times sine of 60. But you got to be careful. It's pointing in a negative y direction, so I have to attach that sign later. It's negative. And if I work that out, that's going to be negative 17.3 newtons. Okay, that's probably the way I'd recommend doing it because we almost always use that reference angle, right? The 60 degrees. If you really wanted to do it the other way, you could. So now you would extract this, this triangle out. Where this is W, this is now WY, this is WX, this is 20. Now this is 30 degrees. But now see if you do it this way, see how the X component now is opposite that angle. So now you need to use sine, right, to figure out WX, because sine of 30 would be opposite over hypotenuse. So then WX would be 20 times sine of 30 degrees. But that still gives you the correct answer, right? Sine of 30 is the same as cosine of 60. Remember before we were able to use cosine, but we had the reference angle 60 degrees. But it turns out cosine of 60 is equal to sine of 30, right? So this will give you 10 newtons. And then to figure out WY now, since it's adjacent, you could say cosine of 30 is WY over 20. So that means WY will be 20 times cosine of 30 degrees. But remember, it's negative because it's pointing downward. And then that's going to be negative. Again, you'll get the same answer, 17.3 newtons. Because cosine of 30 is the same as sine of 60. So it doesn't matter how you do it, as long as you're consistent. My recommendation, if you feel comfortable, do it however you want. If you're just learning this stuff, then it's probably easier just to always use the reference angle, right? The angle that the vector makes with the x-axis, either positive or negative, depending on what quadrant you're in. If you use a reference angle, then the x component will always involve cosine and the y component will always involve sine. Okay, last question. Which quadrant is vector a plus b minus c in? Well, we can do this just by kind of, we don't need an exact answer, right? So we can do this just by adding it graphically. So if I start with A, I want to add B. So I'm going to move the tail of B to the tip of A. So it'll look something like this, right? This is B. And then if I want to add, remember, so A plus B minus C is the same as A plus B plus negative C. And negative C, if this is C pointing up, then negative C will have the same length but point down, right? It'll look something like this. So if I move the tail of negative C to the tip of B now, because I'm adding all these, it'll look something like this. So my resultant vector, I call this R, is going to be, well, I'm drawing from the tail of A to the tip of negative C. It's going to be in that fourth quadrant, right? So in this case, all right, R, which is equal to A plus B minus C, is in the fourth quadrant. All right, and that's it for that particular practice set. Thank you.